So my name is Vlad, and I'll share my experience with an attempt of doing linear algebra the right way. So as an example, I took this book. Probably some of you are familiar. It's called Gone with the Wind. So in this movie, like 80-year-old movie, you see two main characters, Scarlett O'Hara and Red Butler. They meet here the first time. So what I did, actually, after playing for some time with machine learning, I figured that, well, that's how machine learning code looks like. That's Fortran. That's how it looked in 1980, in 1970, maybe in 1956. And that's what people do now, except that they call this code through like several jumps from their Java or Scala. So I decided, let's do it better. So let's get into paradise. We have to have everything immutable, strong types, have maps, not loops, have filter, not loops, and have reduce, not loops. So that's like a good idea. So that was my ideal. That was the paradise I was trying to get into. So more, if you are dealing with linear spaces, right, you have a category. You have a category of linear spaces. Every space is an object in that category, and arrows in that category, morphisms, are linear transformations that are also called matrices. They're slightly different, but it doesn't matter now. Do we have a monoid in a category of n functors? No. There's no monad here. Well, I mean, like in my talk. So I applied the method known as word2vec, which consists of these operations. Read the text, like Gone with the Wind. Like, I'm going to have lots of money, and when I do, I'll never be hungry or cold again. That's a famous phrase, right? We split the whole novel into words and kick out stop words so that after normalization, we'll have money, never hungry, cold again. Kind of preserve the meaning of it, but it's not about the meaning. I'm not getting into the meaning. I'm trying to do linear algebra. So the algorithm next represents each word as a point on a unit sphere. Of course, like multidimensional unit sphere, maybe 100-dimensional, maybe 10-dimensional, not 2-dimensional. But for the purpose of just demonstration, I put them here, like the word hungry, damn, red. Well, these words are also famous in the novel, but they don't encounter in this phrase, right? So we put them randomly. So that's step one. Randomly throw all these words. It's about 16,000 words in the novel. And then do something about them, namely, if the words are close, like hungry and never, they're close. So they are a little bit like nudged together. If they're not, they could be like nudged away. Well, that's a variant of the algorithm. Actually, in this case, I don't do that. So we have these words. After nudging, we have that stuff, like hungry gets closer to never, to cold, to money, to again. And money, again, never, cold are also getting closer to hungry. Why? Because in this n-gram, money, never, hungry, cold again, these words are close. And if the two words are encountered like many times close, so they're getting closer. Of course, if you have just two-dimensional space, they will be all in one dot. But in multi-dimensional, like 100-dimension, they will move around randomly, so we won't have that trivial solution. Now, we are supposed to be like functional Scala programmers. So how do we represent vectors? Ideally, it's something like this. So nudging consists of taking like one vector, well, taking another vector, and we move in that direction. And coefficient with which, like the rate with which we are moving. And we return this vector with like some movement in that direction. Well, the thing is that what do we keep inside? We keep an array inside. So Scala array, Java array, doesn't matter. You have to check the dimensions, and you do this loop, right? So that's OK. This is how you do it. But I was confused by dealing with those like dimension checkings, right? So is it Python? Is it Java? Is it Fortran? All the time, when you add vectors, you have to check, like, oh, do we add the right stuff to the right stuff? Well, otherwise, we can add two-dimensional vectors to three-dimensional. The idea that they're like subtypes. One is a subtype of other. This is the wrong idea, because we are in a category, different types. So in real life, in math, these types are different. And in this category, we have to keep in mind that they're totally different things, but not in Scala, because not an array is just an array. We don't have dependent types. It's not AGDA. We cannot have like a type of an array of length n. But what we have is path-dependent types. So with one more trick, we can make a vector, not just like an individual container of an array, but a vector in a linear space. And that linear space is an instance in which vector is a type. So that's how it is. Linear space, vector space is kind of a synonym in this specific context in my talk. So we define a case class vector space with a certain dimensionality. So like n-dimensional space, and hey, hello. Oh, you are right. So we check that dimension is positive, so not dealing with negative dimensions or fractional or irrational. And we have this trait vector. OK, it's an index sequence with special function, meaning that given an index, it returns a value, right? But the length of that vector is the specified dimension. And you cannot mix vectors from different spaces because they belong to different instances. So in reality, I have two implementations of that vector, of that trait. One is on function. So given a function, just this is a vector, but it's in this space. So we can only take this specific like components, 0 to n minus 1. Or on an array. So we have an array somewhere inside, right? And we take a value of that array like this. If we are immutable, so that's all you need, right? Apply, and you implement things like nudge and whatever, having this apply method. So we have vectors, and we are safe. We are good. And now dimensions cannot be mixed. Like this is an example that won't compile. We have a vector from three-dimensional space R3, and another vector from R3, and a vector from R2. We can like safely multiply vectors by a scalar. We can add vectors from the same space, like the 3D is there, but we cannot add a vector of a two-dimensional vector to three-dimensional, or three-dimensional to two-dimensional. So I feel happy. And really, when I switched to this, I found a bunch of bugs in my code when I did mix vector from different spaces, like 10 dimensions, 100 dimensions. It's like people make mistakes. But now my compiler won't allow it to me. So what happens next? If we store our vectors in that cloud, I mean like first on the surface, and then they're being nudged together, we'll have this kind of cloud. So to reduce dimensionality and to be able to see what we have, we do this thing called PCA, principle. Oh no, we begin with the cloud, but then when we do this, some vectors like get closer, some not. So we have maybe not so many dimensional cloud, and it will look something like this, except that we have like 100 dimensions. So what do we do with this? We want to turn this cloud, turn this galaxy the right way. So that's what PCA, principal component analysis, does. That's again a linear algebra trick that rotates our galaxy and presents it in the right way. How does it do it? We need eigenvectors and eigenvalues. Eigenvalues are sizes of our cloud in the biggest, like in all the different dimensions, where they're like specifically big. Like the biggest eigenvector is where our cloud is the longest. Then the second is where our cloud is the widest. Then the next one is where our cloud is the tallest. I believe like 3 is enough for human beings, right? So that's what we do. The trick is to find these eigenvectors, to find how big are those eigenvalues. But, well, that doesn't matter. We have to find 3 eigenvectors, or maybe 2, and rotate our cloud. To rotate the cloud, we need to do linear transformation. But before that, we need to find eigenvectors. So PCA does it by multiplying matrices, and eventually we do that. But see, yeah?
Question. So you're doing the nudging in a function way.
Yeah.
Isn't that very, very, very memory inefficient? Especially
Yes, it is. I'll get there, yeah.
You'll get there.
Well, with vectors, like, we don't have so many vectors, but later with matrices, it will be really hard, so I'll get there. So, but we need matrices now. How do we represent matrices? We're kind of lucky. We already have vector spaces. What's a matrix? A matrix is an arrow, a morphism from n-dimensional space to m-dimensional space. So a matrix is declared as this. So we have a domain. That's where to which matrix is applied. And we have a codomain. And it extends what? Just a function from like a pair of indices to a double value. So that's how it is. We have this index like I and G, and it points to a value inside that matrix. And it we also like is like quirks of Scala. So we pass the types, but we also have to pass instances, domain and codomain. So inside the matrix, you can multiply a matrix by a certain vector from domain, but not, generally speaking, not from codomain, unless they have the same dimensionality. So that's how it is. Like we have a matrix has a method, multiply by vector, meaning like multiply vector by matrix with matrix on the left. So the vector is from domain, the result would be a vector in codomain. So we go from one linear space to another. And how do we calculate the data? Well, basically the same thing, just add the components, right? So like no magic here. And I transform it to array and push it into the vector, because vector, one kind of a vector is when it's instantiated from an array. It's not necessarily because if you can have a function, you can pass a function and nothing is instantiated, so no big deal. You can compose functions and basically keep just one reference. But this way, I have, because I fold, so I have to store the vector. Transposing a matrix is very trivial because this is just a function that you pass. We really don't even instantiate anything. We take an original matrix, which is like domain, codomain, and produce a matrix that has codomain domain. And what we have, it's a matrix on a function. That's it. Zero memory taken. Well, because we do just transpose. So in real life, when we do something bigger with matrices, well, we do take some space. But if we do that, and we flatten the whole picture, all those words from that sphere, 100-dimensional sphere, we can flatten and we have this two-dimensional representation. And let me show you. Here we have Red Butler, that guy to whom Scarlett was married. Here's Scarlett. What's around Scarlett? Like love, mother, money, except Red is surrounded by, Butler is his last name, dead, eyes, world, man, Yankees, and so on. Child, by the way. Child is not close to Scarlett. I would say probably it means in the novel that she didn't care much, but Red did. Well, he actually did. So that's how it is. And they're not so close. So they're not like very close as personalities. So you see it just by analyzing, by just like rotating matrices and analyzing. I don't know what's this. So what you see in the picture. So from this book, we extract this like chunk of knowledge. So that's good. If you have like pretty nice, well-formed cloud, but what if the cloud is not that well-formed? What if you have like two flat clouds, one on top of each other? So they'll be flattened like this. The words that are actually not that close, they can be flattened, projected, and we wouldn't like that projection. So to check that case, I created an example, which is like this. So this is a shape that I rotated in 3D, so it's a 3D shape. And see, in one of the projections, this butterfly is just a cross. And if you take these coordinates, and instead of just rotating, take these coordinates and try to find eigenvectors and eigenvalues, they will be, you'll find that the projection would be just that cross. So that's no good, because see how far away are those edges, sides of those wings, right? So something should be done. So that something is a nonlinear method, is called summon dimension reduction. So basically that's what it does. Like we have this flat projection and it pulls apart the things on the wings that are close. So that's what it does. Like we have what we do. For every pair of points, we know whether they're close in the original space or not. Even in the projection, we have this original matrix of distances, right? So what we need to do, we need to make sure that our representation, our projection, is kind of close to that representation in the original space, except that here we had like 3-dimensional, and we flatten it to 2-dimensional. But in real life, we'll have 100-dimensional, and we have to produce 2-dimensional. So what does it mean? Like 100-dimensional space, and with all the points, how many points? Like 16,000 points. So we need to have a matrix 16,000 by 16,000, 256 million. So that's like a gig, right? Or half gig, something like that. Well, why half gig? Because we calculate only the distance. Whether the space original was 100-dimensional or million-dimensional doesn't matter. All we have is just points and distances with them. And what we need is to pull these points away. To pull, meaning that we have to have this gradient descent towards having better representation of our original distance matrix. So that's what we do. This is like what my program produces, well, because I'm not good with graphics. So this is just alphanumeric output. So summon algorithm, I'll show you how. So summon algorithm does it like this. First, you have this like abstract cloud. First, you do PCA, 50 steps, meaning like 50 rotations of the matrices to find something like close to eigenvectors. And then 300 summon steps, and from this projection, we have that. Well, it's not a projection anymore. It's a representation. It's mapping, because it's definitely not linear. But the thing is, we'll have huge matrices, like half gig or gig each. And imagine you do it like in a functional way, meaning like copy, right? So, well, copy is no good. So again, like this is the description of what a summon algorithm does. So we build distance matrix. We run PCA in the beginning so that we find like more or less good dimensions and take the first 2 or 3 dimensions. And then in this 16K dimensional space, meaning the number of points, right? So we optimize it using gradient descent, minimize the distance between original vectors. Like the distance between the matrix of original vectors and current distance matrix in just 2D. So we try to approximate the original matrix as much as possible by moving points on our 2D. So the challenge was like, well, why is it 128? Well, because the matrices, distance matrix is symmetrical, right? So there's no need to keep like the lower triangle. Still like almost a gig. So we don't want to do like copy and paste. So I sighed and decided, okay, let it be mutable. So nudging and addition will have this like plus equals. And we keep the vectors over there, even for those small vectors, but we have just 16,000. So it's not like a quarter, eighth of a million, of a billion. So we do this. OK. The trick with those algorithms is that all of them are parallelizable, even with mutability. Summon can be, well, because we are doing those nudges, like nudge here, nudge there, they're totally unrelated. So they're getting together. So basically, I run it on all the cores I have, even with this mutability. Just like a choice or choice of algorithms. Even summon, OK, so they like all those points are moved around like separately. So that's cool. The other thing is with performance of addition, right? So we're in Scala. Scala is on top of Java. So what happens? Like we take an I, Java array, like do something in Java array. Java array checks the index, returns a Java double, a primitive type, a primitive value. That double is boxed into object double, and it's given to Scala code. Another double is also returned from array and boxed into a double. In the code, when we do addition, like both are unboxed, added, boxed again, and stored. So I was wasting like tons of whatever time on these funny operations. Yeah, you can ask me like, can you do specialized? Yeah, I can. It just helps a little bit. So I decided, okay, let me create this like layer of Java below our like type safe code, a layer of Java that doesn't check anything. I mean, it does check, but it doesn't check that the vectors are of the same size because they're called from a good code that knows all those dimensions, right? So nudge is written in Java, class folding2 does all those folds for any operation. So all this like Scala product of two vectors is done here. So that's how it is, but I hide it. So it's not supposed to be visible to user because like if you are a user, if you design an algorithm and do this like raw calls, you can be confused easily. I was. So instead it's just hidden. It's like another layer. And on top, it's a good Scala. So that's how nudge works from Scala. So if we are on array, mean that there is like a Java array inside. So we call this array ops nudge. On the other hand, if it's not an array, meaning it's just a function, so something like multiplied by whatever, like by a scalar, so the same vector with no with no value there. So we do this operation like multiplication and whatever, and addition. And these two, like what's addition? It's several times faster. Well, of course, if you tell it to Java people, they would not care about types because they, like, in a sense, they don't care much about types. We do. So it works, it's fast, but it's under the thick layer of good type-safe code. So what did we do? I tried to do LA functionally. Yeah, and I do LA functionally, but on a certain level. There are like layers below. So the example was word2vec, and I applied PCA, dimensionality reduction, and summon dimensionality reduction. But to be like real, so I have to keep stuff mutable and do all these operations through Java. And also, when I started it, I was just like a free, whatever, flying, floating, a guy that had time to do that. Now I'm in Salesforce. So here are the talk that our guys are giving now, so including right now. So I'm doing like machine learning and all this stuff at Salesforce now. This was totally unrelated. So, any questions? Yeah.
So if you moved to Java because you were concerned about performance and you figured immutability could be sacrificed, why stop at Java? Why not put that down in C++ or something?
We could, but calling natives is kind of just not something I am comfortable with. But yes, that's on one hand. On the other hand, if you ever saw native Scala being compiled, like Scala being compiled into like LLVM, into native code, and running, and
I'm not talking about compiling Scala down to Scala native. I'm saying that portion that you want to be very performant, that part you wrote in Java.
Could be.
Why not write that in C++ or?
Well, see. Let me finish. See, Scala native compiler produces like a pretty efficient code these days, right? But I saw a competition like in Scala, in our Scala meetup a while ago. So the same piece of code running in native Scala, in Scala compiled to native. So it's pretty efficient in the beginning. And the same code running on JVM. In the beginning, it's like slow, like starting, but then it beats everything. Why does it beat everything? Because JIT does re-optimize the code so that a human probably cannot write this kind of code. well, some people say that, yeah, we are superhumans and we can beat. Well, I don't know. That guy also like produced the pretty efficient code. But so currently, I kind of rather believe that JVM, like eventually during this reoptimization, may produce something that a human cannot produce. So that's why I stopped here, and I didn't go there. But maybe, well, the other thing is like, why not use graphic GPU, right? That would definitely be much faster. But well, I'll play with it maybe. Yeah.
Any other questions?
Well, I have one. Are you saying that Scala is just not efficient for matrix operations?
Yeah, that's what I said.
You didn't try sparse matrix operations. Did you try to model this as a sparse matrix?
Sparse code?
Sparse matrix.
Sparse, well, see, in this case, these are not sparse matrices.
Right.
Everything's filled, so all this like big distance matrix, it's all, well, it's not sparse. In this like PCA, those rotation matrices, right? They're not sparse, so there's nothing to do with sparse matrices. Of course, if they're totally very sparse, like mostly zeros and like values here and there, yeah, that could make sense. But again, it would be pretty doable.
Okay. So did you do any of the standard benchmarks on your LinPack?
Well, I did have it. I was comparing like this code with my code, but with different version, like Java version and like specialized version in Scala. So basically, specialized version is twice slower than this Java layer. Plain Scala without like specialized, it's like about 8 times slower. I didn't compare it to anything else, basically, well, because like this PCA algorithm, I wrote it myself. I don't need all eigenvectors. I need just 2 or 3. So why would I bother to use those algorithms that?
Okay. So, is everybody happy with linear algebra in Scala? It's not the best thing.
Or rather not, right?
All right. Thank you very much.
Yeah, thank you.